staff proof that's generated by the Cairo prover into the staffware staff verifier. So you can see here is a software staff verifier, and actually you want to submit a staff proof into this. You need to split it into many different parts, smaller parts, and submit each part into four main smart contracts. And you can see here, like first you need to submit three proof for verify Merkle, and about seven proof for verify FI, and some proof for verify I mean, like uh, continuous page part, and finally the final proof into the proof and verify proof and register. So now I will talk about how to split the big proof into different parts. So uh, yeah. So I will talk about how staff works. So first we have an execution tray. So here, and you risk Solomon encoding that into execution tray low degree attention, and then you will commit, you Merkle commit it. So here is the first proof that you need to send is for the execution tray, like the Merkle commit proof for the execution tray. And in the Cairo prover, you have something like for you need to ensure about the permutation argument and evaluation argument. So you need some extension columns. So I will call here like uh, extension trace. And you also need to resume encoding that into low degree attention, and you to Merkle commit it. So here is a second proof that's sent to verify Merkle. So next we have composition polynomial that you compile many constraints, Jensen constraint and boundary constraint into the composition polynomial, and also you use Reed-Solomon encoding that and into the low degree attention, and you also need to commit that using Merkle tree. So here is a three Merkle trees that you use in a Cairo prover. So you need to send the proof from it into the smart contract. So here's why we have three proofs sent to the verify Merkle smart contract. So next we have next you will use diff method, right? Diff method, and finally you get the quotient constraint with the form of this. Yeah, and so you need to you use FRI to prove that. Okay, so use FRI. So actually, each verify FRI smart contract here, you only verify one layer from the FI tree. So if you have FI here, we have about like 7 layers. So you need to send to the 7 proof for it. So that's the reason why we need to hear the 7 proof for the verify FRI. So next is register continuous, which is about is for like like for the memory. because in the chiral prover we need to the memory is not put in like a random access memory. It has to put in I mean like continuously. So we need to send all of this into the smart contract. So that's why we need send some proof into this one. And finally, the verify proof and register we need to so here we need to send the proof of that we use the deep method here correctly. I mean like we need to send some mask and some proof, Merkle proof. A mask here, something like that in the in deep method. So I will dive into each dive into the parameters that you need to send for the main for smart contract here. So the first thing is about Merkle verifier. So yeah, here is you can see here is a parameter that you need to submit on the Merkle verify smart contract. So yeah, so we have some parameter like initial Merkle tree, Merkle cube. Right, so suppose that we have a Merkle tree like this one. And so here the initial Merkle cube including two terms like the position and the value. For example, if you want to send the proof of this one, of this position into the smart contract, so I suppose that the position here is I, and the value here I call it AI. Here is A. And next we have Merkle view. So Merkle view, there is two terms like sibling values and the node. So for example, you want to prove that this one is a sibling value here, and also the node that you need to send is this one, right? So it's a node. And also the height of the Merkle tree. So here is 2, and finally is the expected root. Is this one is the expected root. Yeah. So next is FRI verify. So actually it just verify only one layer. So we need to send information of each layer into this smart contract. So so here is the parameters of the FRI layer. So first thing is FRI step size. This one is a logarithmic size of the FRI step. So you think like, for example, you want in FRI you want to fold it into from one this, right? So basically you choose two node, and you fold that into only one node. So the step here is only 2. So the log size here is 1. But in chiral prover they often choose a FRI step size is 3 because they don't fold like two nodes into one, but they choose like 8 nodes right here, and they fold all of this into one node in FI step. So the log size here often equal to 3. Yes, so next is the expected root of FRI, and so here, for example, you have a equation of FI like this. So here is, we call it evaluation point. Point in this one, and in the FRIQ, we have the position. For example, if you want to prove this position, right? So, and the value of it, the value of this position, and also the inverse. Because in this equation, you need to divide the polynomial into x, right? So you need to send this in here like 1 plus x. So this is the information of the FRIQ parameter, and finally the proof here is the Merkle proof in FRI. The proof here, like the proof that the structure of this proof in FI is same that the structure of proof in Merkle verifier. So yeah, that's the parameter that you need to send to FRI verifier. So next we have register continuous batch. So here is, for example, if you can see here like because the memory that used in chiral prover, we need to put it into continuous. Like, so we also need to send it like the start address and also each value of the memory. So, and the parameter like alpha and z and prime here is used for compute the cumulative product of this memory. So that's the meaning of all parameters. So finally, so here is the parameter of that we need to send into the final smart contract. Like, I will talk briefly like some. First, we have the proof param. So the proof param here, including like the number of query, in the FRI query space, and the logarithm of the blow-up factor. Something like the number of FRI steps, and here is FRI step for each layer. So we also need to, because to ensure the bit of security. So in the chiral proofer, we need to do something like proof of work. So here we need to send the proof of work security bit in this proof paragraph. Yeah. So next is the proof. Like we need to send 3 Merkle commitment. three Merkle complement of three Merkle tree here. So the out of domain value and the norms that used for proof of work process, and need to send the mask for the deep method here, and finally the proof of the mask. So yeah, that's all for my talk. Thank you.